Hello and welcome back to Math 1324. We are still in Chapter 5, Linear Inequalities and Linear Programming, and we are doing the last section, Section 5.3, titled Linear Programming in Two Dimensions, a Geometric Approach. These first couple of pages are very reading intensive, so to just get through them, and then we will walk through a few examples. Okay, a linear programming problem. Oops. Linear programming is a mathematical process that's been developed to help management in decision making. An intuitive geometric approach will be used in this section. Insight gained from this approach will prove invaluable when we consider an algebraic approach that is less intuitive but necessary to solve most real-world problems. A linear programming problem is one that is concerned with finding what's called the optimal value. So it's either going to be a maximum or a minimum value of a linear objective function of the form z equals ax plus by, where a and b are not both equal to 0. And the decision variables, which are x and y, are subject to problem constraints in the form of either greater than or equal to or less than or equal to linear inequalities and equations. In addition, the decision variables x and y must satisfy what are called the non-negative constraints. In other words, x greater than or equal to 0 and y greater than or equal to 0. And if you'll remember, those two constraints restricted us to the first quadrant when we're graphing. All right, the problem constraints are limits imposed by available resources on a manufacturing company. For example, you may have constraints with transportation costs, environmental protection laws, maybe the availability of parts, or interest rates, or plant capacity, or even the demand. So those are going to be your problem constraints. Okay, the set of points satisfying both the problem constraints and the non-negative constraints, remember that's that x and y can't be negative. The set of all points satisfying those things is called the feasible region for the problem. And in the last section, we learned how to find that feasible region. All right, any point in the feasible region that produces the optimal value of the objective function over the feasible region is called an optimal solution. A mathematical model consists of the objective function to be optimized, the problem constraints, and the non-negative constraints. So we're going to go look at a mathematical model here in just a minute. Couple of theorems. Theorem 1, fundamental theorem of linear programming. If the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the corner points of the feasible region. That's going to be huge when we go to try to find the optimal value. We're going to first find the feasible region, then we're going to locate the corner points. Okay, existence of optimal solutions. If the feasible region for a linear programming problem is bounded, so if you have a bounded feasible region, then both the maximum value and the minimum value of the objective function always exist. If the feasible region is unbounded and the coefficients of the objective function are positive, then the minimum value of the objective function exists, but the maximum value does not. So that's if the feasible region is unbounded. And the last part, if the feasible region is empty, in other words, there are no points that satisfy all the constraints, then both the maximum value and the minimum value of the objective function do not exist. All right, let's go talk about the procedures. Constructing a model for applied linear programming problem. Step 1, you've got to introduce the decision variables. Step 2, you've got to summarize relevant material in table form, relating columns to the decision variables if possible. Step 3, determine the objective and write a linear objective function. Step 4, write problem constraints using linear equations and/or inequalities. Step 5, write your non-negative constraints. All right. How do you use the geometric method for solving a linear programming problem with 2 decision variables? Once you set your problem up, the next step is to graph the feasible region. If an optimal solution exists, according to that theorem 2, you need to go find the coordinates of each corner point. So you've got to locate the corner points. And I'm going to encourage you to construct what's called a corner point table that lists the value of the objective function at each corner point. Then determine the optimal solutions from that table. And for an applied problem, you need to interpret those optimal solutions in terms of the original problem. Okay, now we're going to go look at some examples. On these examples, or this first example, everything is set up for you. It tells you to optimize the objective function subject to the given constraints. You want to maximize p equals 3x plus 2y, subject to 6x plus 3y less than or equal to 24, 2x plus y less than or equal to 16, and the non-negative constraints x greater than or equal to 0, y greater than or equal to 0. So let's go find our feasible region. Okay, first inequality, 6x plus 3y, I'm going to say equals 24 because I'm going to graph the corresponding equation. And I'm going to do that by finding my intercepts. If y is 0, I get 6x equals 24, so x would be 4. And if x is 0, I get 3y equals 24, so y would be 8. For my second inequality, 2x plus y less than or equal to 16, if I wanted to graph that line, if y is 0, 2x equals 16, so x is 8. And if x is 0, I get y equals 16. Okay, for the first inequality, let's go graph the boundary line. I need to plot the point 4, 0. I'm going to let 1 be, hold on, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. All right, here we go. 4, 0 and 0, 8. There's my first boundary line. Now, which one do I want to shade? Do I want to shade down here? Or do I want to shade up here? How do you know? I'm going to go pick a test point, 0, 0, and plug it in to my inequality. 0 less than or equal to 24, that is a true statement. I want to shade the half plane that contains 0, 0. So I want to shade here. All right. Now for the second line, I had the point 8, 0, and I have the point 0, 16. All right. If I pick a test point, let's say 0, 0, and I plug it in here, I would get 0 less than or equal to 16. That's a true statement. So I want to shade 0, 0. So my feasible region is going to be the region, hold on. Remember that the feasible region is the region that satisfies both of those inequalities. So the yellow region satisfied the first one, the blue region satisfied the second one, and the green satisfies both. So my feasible region is there in green. All right, the feasible region is in green. What are the corner points of my feasible region? I'm going to do those in green here. It's going to be 0, 8, 0, 0, and 4, 0. Let's go list those as my corner points. Corner point is 0, 8, 0, 0, and 4, 0. Now I'm going to plug those corner points in to my optimal function, 3x plus 2y. So my objective function is 3x plus 2y. So 3 times 0 plus 2 times 8 is 16. 3 times 0 plus 2 times 0 is 0. And 3 times 4 plus 2 times 0 is 12. Which corner point maximized my objective function? And the answer is the point 0, 8. Number 2, we want to optimize the objective function subject to the given constraints. Minimize p equals 2x plus 4y, subject to the inequalities x plus 2y greater than or equal to 10, 3x plus y greater than or equal to 10, and x greater than or equal to 0, y greater than or equal to 0. Remember that those are your non-negative constraints. These two things restrict you to the first quadrant. All right, let's go graph the boundary line for x plus 2y greater than or equal to 10. The corresponding equation is x plus 2y equals 10. If y is 0, x is 10. If x is 0, 2y equals 10, so y is 5. I have the point 10, 0, and 0, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5. All right, so I have the point 10, 0, and 0, 5. There's that boundary line. Which way do I want to shade? If I pick the point 0, 0 and plug it in up here, I get 0 bigger than or equal to 10. That is false. I do not want to shade this point. So I'm going to pick to shade up here. Okay. The second inequality, 3x plus y greater than or equal to 10. To graph the boundary, 3x plus y equals 10. If y is 0, I get 3x equals 10, so x is 10/3, or 3 1/3. If x is 0, y is 10. So there's 6, 7, 8, 9. Whoop. So I have the point 10/3, 0, so 3 1/3 was about right there. And I have the point 0, 10. So my boundary line is there. Okay, which way do I shade? Do I want to shade 0, 0? If I pick 0, 0 and plug it in, my test point is 0, 0. I would get 0 bigger than or equal to 10. That's false. So with respect to that purple boundary line, I do not want to shade 0, 0. So I'm going to go shade this way. Now, my feasible region has to be colored both yellow and blue. Remember that yellow and blue make green. So the feasible region that I'm looking at is unbounded because it keeps going this way, both ways. All right, so my corner points for that feasible region will be 0, 10, what else? 10, 0, and I'm not 100% certain, but I'm thinking 2, 4. How can we check that? Would 2, 4 satisfy both this equation and this equation? Let's see, 2 plus 8 is 10. 6 plus 4 is 10. Yes, so that is the intersection point of those two boundary lines. You could also go do 1, 2, 10, 3, 1, 10, and go RREF it on your calculator. And if you did, you would get 2, 4. All right, we have 3 corner points. Now let's go plug those corner points into my objective function, which is 2x plus 4y. So 2 times 0 plus 4 times 10 is 40. 2 times 10 plus 4 times 0 is 20. And 2 times 2 plus 4 times 4, 4 plus 16 is 20. Okay, I'm trying to minimize the objective function. The smallest value occurs at those two corner points, at 10, 0 and at 2, 4, here and here. Let's look at one more example and let's do a real world problem. So production scheduling. A furniture company has 2 plants that produce the lumber used in manufacturing tables and chairs. In 1 day of operation, plant A can produce the lumber required to manufacture 20 tables and 60 chairs, and plant B can produce enough lumber required to manufacture 25 tables and 50 chairs. The company needs enough lumber to manufacture at least 20 tables and at least 500 chairs. If it cost $1,000 to operate plant A for one day and $900 to operate plant B for one day, how many days should each plant be operated to produce a sufficient amount of lumber at a minimum cost? What is that minimum cost? Okay, that's a lot of information. I got that there's plant A and plant B, and I got that they're making tables and chairs. I encourage you to push pause for a minute and reread this problem. Okay, it's wanting to know how many days should each plant be operated to produce a sufficient amount of lumber at the minimum cost. And to minimize that cost, what is that minimum cost? So we're going to let X be the number of days of operation of plant A, and let Y be the number of days of operation of plant B. Okay, it cost $1,000 to operate plant A per day and $900 to operate plant B per day. So your cost is going to be 1,000 times the number of days you operate plant A plus 900 times the number of days you operate plant B. That's how you get your objective function. Okay, what are your constraints? Obviously, the number of days that you operate plant A and plant B has to be non-negative. Okay, where did this one come from? Okay, for tables, plant A can produce enough lumber to get 20 tables per day. Plant B can manufacture enough to get 25 tables, and you need at least 200 tables. So that's where that 20x plus 25y greater than or equal to 200. For your second one, plant A can manufacture up to 60 chairs, plant B 50 chairs, and you need at least 500 chairs. So that's where you get 60x plus 50y greater than or equal to 500. Let's go find the feasible region. All right. The first inequality, the boundary line will be 20x plus 25y equals 200. If I let y be 0, 20x equals 200. So x would be 10. If I let x be 0, 25y equals 200. So y would be 8. For my test point, 0, 0, would 0 be bigger than or equal to 200? That is a false statement, so no. Okay, I'm going to go graph that boundary line. I'm going to let each tick mark be a half. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I have the point 10, 0 and the point 0, 8. There's my boundary line. And I do not want to shade 0, 0. So I'm going to shade my yellow is going to be up here. All right. For my second inequality, 60x plus 50y is equal to 500. Graphing my intercepts, if y is 0, 60x equals 500. So x would be 500 divided by 60. Okay, 500 divided by 60 is 8 1/3. And if x is 0, I get 50y equals 500. So y is 10. I have the point 0, 10, and I have the point 8 1/3, 6, 7, 8 1/3. My boundary line is here. Now, if I plugged in 0, 0, I would get 0 bigger than or equal to 500. That is false. So I would not want to shade 0, 0 when it came to that purple boundary line. So I would want to shade this way. All right. The green is my feasible region. My corner points will be 0, 10, 10, 0, and I'm not real certain right here. To find that, I could go on my calculator and RREF 20, 25, 200, 60, 50, 500. Let's go RREF that. Second matrix edit. It's a 2 by 3. First row is 20, 25, 200. The second row is 60, 50, 500. If I go second matrix math and go up to RREF, hit enter, second matrix enter, 5, 4. Now, on my graph, I couldn't really tell that. Here's 5, 4 right here. So anyway, it's a little off. But that point of intersection is 5, 4. Okay, I want to go find 1000x plus 900y at each of these corner points. So 1000 times 0 plus 900 times 10 is 9,000. 1000 times 10 plus 900 times 0 is going to be 10,000. And then 1000 times 5 plus 900 times 4. Let's go see. 1000 times 5 plus 900 times 4 is 8,600. What were we supposed to do? We're supposed to minimize. We want the smallest value of those three. The smallest is here. So to answer my question, how many days should each plant be operated? Plant A should be operated for 5 days. and plant B should be operated for 4 days. The minimum cost will be $8,600. And that's how a linear programming problem is done using a geometric approach. Go do the homework problems associated with this section, and until next time, goodbye.